Okay, so the next thing we're going to talk about is multiplying radicals. So unlike adding and subtracting, where you had to have a common or like term, multiplying, you don't have to have like terms. All you have to do is just multiply the coefficients, which are the outside, and then multiply the radicands, which are the insides. Okay, so and then if you can simplify, you'll need to do that. So 4 root 3 times 6 root 2. Notice 3 and 2 aren't the same, but that doesn't matter for multiplying. All you have to do is multiply the outside coefficients. 4 times 6 is 24. And then multiply the inside. 2 times 3, that's root 6. Now, if root 6 could break down, then I would need to do that. But in this case, 2 times 3, that doesn't have any pairs, so 4 root 6 is my final answer. On the next one, I'm going to multiply my coefficients. 2 times 4 is 8. Multiply my radicands. 3 times 15, that's 45. And then I'm going to try to break down 45. 45 is 9 times 5. 3 times 3 times 5. So the 3 goes on the outside. The 5 stays home. The lonely one stays home. Now, don't forget that there was already an 8 out in front. So what happens in that case? Well, the 8 times the outside 3, both outsides, multiply, and that gets us 24 square roots of 5. And that's it. One more example. We're going to multiply the outside coefficients. That's the 2 times the 5, and that gets us 10. Then you're going to multiply the inside radicands and leave them inside. 3y times 2x is 6xy. If 6xy can reduce, which is 2 times 3 times x times y, there is no pairs, so in this case I can't reduce anymore. So multiplying radicals is as simple as that. One application is if you ever raise a radical to its index. Now, raising it to a power just means you're multiplying it several times over. We have this following property. The nth root of a raised to the n is equal to a. Or another way of thinking about that is the n in the index and the n in the exponent just kind of undo each other, and you're just left with the inside a. For example, root 3 times root 3. I'll do it the long way and then I'll show you the rule way. If you did it the long way, root 3 times root 3 is 9, root 9, and root 9 is plane 3. Which I know that doesn't even seem like that long, but I'm trying to get you to understand the rule. So the other way I want you to think about it is if you have root 3 times itself root 3, that's like root 3 squared. And because the invisible index is a 2, the 2 and the 2 undoes each other and you're just left with 3. Either way, you're still really going to get 3. But when the problems get harder, I want you to be able to do it. So the next one's harder, right? Root 7y times root 7y. One way of thinking about that is root 7y squared. And because the index was already a 2, the 2 and the 2 undo each other, and that's just left with 7y. If you wanted to do it the longer way, we could take root 7y times root 7y, multiply the insides and get 49y squared. The square root of 49 is 7, the square root of y squared has a pair, it comes out, and it's still 7y. Now this one, there's no other way you can do this problem with such a long expression underneath a radical. You really want to do it the shortcut way, so that the index 2 and the exponent 2, because there's 2 copies of 5 minus y, the index and the radical undoes each other, and you're just left with the inside, which is 5 minus y. Okay, so this one's already written in the form that you want. So this 5 and this 5, the 5 index and the 5 exponent undo each other, and you're just left with the inside, which is a lot of stuff, but it's not even hard because it's just whatever it is in the inside, which is 150x squared y. Alright, our next problem is the square root of 5 squared. Well, the 2's just undo each other and you're left with 5. And the last one, the 3 index for the cube root of 14 and the 3 exponent undo each other and you're just left with 14. Okay, and that concludes our lesson on radicals.